Imagine a driver has $180 available and taps cash out. Our system sends the transfer request. But the bank's response times out. Now we have a dangerous question. Did the request fail before the bank saw it? Or did the bank accept it and only the response was lost? If we send another transfer, the driver might be paid twice. If we immediately return the reserved money, the driver might spend those same funds again, while the first transfer is still moving. That uncertainty is the heart of this design. We need a system that is fast for the driver, but conservative with money. By the end of this video, we'll build the complete path from finalized earnings to one auditable external payout, and we'll see exactly how it survives retries, concurrent requests, worker crashes, duplicate callbacks, and provider timeouts. Let's define the problem before choosing technology. Functionally, the system has 4 jobs. Trusted marketplace systems give us finalized driver earnings and later corrections. A driver can see available, reserved, and paid amounts, request a full or partial payout, safely retry after a timeout, and check the eventual result. Non-functionally, financial correctness comes first. The history must be durable and auditable. Retries must be safe, and the API should respond quickly without pretending that an external bank has already settled the transfer. We'll design for 5 million active driver accounts, peaks of 5,000 earning records per second, and 500 payout requests per second. A healthy internal system should durably acknowledge a valid payout within 2 seconds. The external transfer may take minutes, or longer. Trip pricing, rider charging, tax, foreign exchange, and bank account onboarding are outside our boundary. We receive finalized money records and an opaque destination reference. And because this is financial data, earning, reservation, release, and payout history must remain auditable for 7 years. The architecture becomes much easier once we state the invariants. First, a driver's available balance can never go below 0. Active payout reservations are not spendable. Second, one logical payout can debit the driver's money at most once and create at most one external transfer. 10 retries must still converge on the same payout. Third, accepted does not mean settled. Our API can confirm that the payout request and reservation are safely stored. It cannot promise that a bank we don't control has already moved the money. This means pending and even unknown are valid states. We prefer telling the driver, we're still confirming this payout, over guessing and accidentally paying twice. The source of truth should be an append-only ledger, not one balance number that we overwrite. 4 durable objects give us the model. A driver account is identified by the driver and currency. Keeping each currency separate avoids hiding foreign exchange behavior inside the balance. Each driver and currency account owns a sequence of immutable entries. An earning entry records the amount, currency, source type, stable source ID, and time. A uniqueness rule on the source identity prevents the same trip earning from being applied twice. If an earning changes later, we append a correction. We never silently rewrite the old record. A payout stores the payout ID, account, amount, destination reference, client idempotency key, request fingerprint, state, and version. Its state moves from reserved to submitted, then to succeeded, definitely failed, submitted unknown, or review required. A transfer attempt stores the provider idempotency key, provider reference, request fingerprint, callbacks, and the latest reconciliation evidence. This separates our internal financial history from our uncertain conversation with an external provider. The same pattern handles payouts. A reservation moves money out of available funds and into reserved funds. A confirmed payout finalizes that reservation as paid. A definite failure appends a release, making the amount available again. So the displayed totals are derived from durable facts. Available money is finalized credits and corrections, minus active reservations and finalized payout effects. The exact accounting representation can vary, but the invariant cannot. Reserved money is not available to another payout. Caches and read projections can make balance screens fast. They are never allowed to decide whether money is spendable. A trusted earnings producer posts an entry with a stable source type and source ID. An exact replay returns the stored entry. A different payload using that source identity is a conflict, because silently changing a financial record would destroy the audit trail. The driver can read available, reserved, and paid totals, page through ledger and payout history, and retrieve one payout by its stable ID. Those reads let the driver recover after disconnecting, instead of depending on one response or callback. The central write contract is create payout. The driver sends an amount, currency, destination reference, and an idempotency key. The server authenticates the driver and verifies that the destination belongs to that account. Inside the financial transaction, we store the idempotency key with a fingerprint of the request, such as the amount, currency, and destination. If the same request is replayed, we return the original payout ID and its current status. We do not create a second payout. If the same key is reused with a different amount or destination, we return a conflict. That usually means a client bug, and silently accepting it would make the key ambiguous. After the reservation is durable, the API returns a stable payout ID and a status such as reserved or pending. A 202 response means we accepted responsibility for the workflow. It does not mean the bank has settled it. A production service would expose more operations, but these contracts cover every requirement in our core journey. At a high level, the system has two paths. The first is the durable acceptance path. Trusted earning producers write through a ledger API into the transactional account store. A driver's request reaches the payout API, which uses that same authority when it reserves funds. In one transaction, the payout API checks the current available amount, creates the payout, appends the reservation, and stores the client idempotency record. That transaction is the end of the synchronous path. Once it commits, the API can return a stable payout ID within our 2-second target. The second path is asynchronous external settlement. After the commit, transfer work reaches a queue. A worker claims the payout and calls the external payment provider. Provider callbacks enter through an authenticated adapter. Balance, history, and payout status reads can use a versioned projection for scale. But if that projection is 1 second behind, it is only a display issue. Every reservation still goes to the current authoritative account state. The driver does not wait for an external network round trip before receiving that durable payout ID. Accepted does not mean settled. This base design is intentionally incomplete. 3 failures remain visible. Concurrent requests can race for the same balance. A database commit can be separated from queue publication by a crash, and a provider timeout can leave the external outcome unknown. The deep dives will repair those gaps one at a time, without moving the components the viewer already knows. Let's follow a successful $100 payout from an available balance of $180. Step 1. The request reaches the Payout API with a new idempotency key. Step 2. One database transaction verifies the driver has enough available funds. It creates payout PO917, appends a $100 reservation, stores the request fingerprint, and writes an outbox row. After that commit, the driver has $80 available and $100 reserved. The API can safely return the payout ID. Step 3. The dispatcher publishes the outbox row. If it crashes, the row remains unprocessed and will be published later. Step 4. A worker claims the payout and calls the provider with a stable idempotency identity derived from PO917. Worker retries always reuse that identity. Step 5. The provider reports success. The callback adapter authenticates the event and deduplicates its provider event ID. Step 6. A final ledger transaction appends one uniquely keyed payout effect, clears the reservation, and marks the payout succeeded. Now the account shows $80 available, 0 reserved for this payout, and $100 paid. Replaying the callback changes nothing because the final ledger effect is unique to PO 917. Why add an outbox instead of publishing directly to the queue? Because the database and queue are two separate systems. If we commit the reservation and crash before publishing, the driver's money can remain reserved forever with no transfer work. If we publish first and the database rolls back, a worker could send money without a valid reservation. The outbox closes that gap. The payout, reservation, and dispatch intent commit together. A separate dispatcher may publish the same outbox item more than once, and that is okay. The queue consumer and the provider call are idempotent. This design does not require magical exactly once messaging. It requires durable intent, stable identities, and replay-safe processing. Now, suppose the driver uses two devices, and both request the full $180 balance at the same time. Both may read the old displayed balance. That is fine. The decision happens at one authoritative account boundary. Each transaction checks the current account version and available funds, then conditionally appends its reservation. Only one can commit against the same version. The losing request reevaluates the new balance and receives insufficient funds or a conflict. We never rely on whichever API server happens to run faster, and we never use a cache as the lock. There are also two different idempotency boundaries. Client idempotency maps one driver request key to one payout and rejects a changed payload. Provider idempotency maps that payout ID to one external transfer operation. A worker lease or claim version helps prevent two workers from doing the same work at once, but leases can expire during a network call. The stable provider key is still essential because every worker retry must refer to the same transfer. That is how concurrent requests and retries converge on one reservation, one payout, and one external transfer identity. Now return to the timeout from the opening. The worker sent the request, but it cannot tell whether the provider accepted it. The payout moves to a submitted unknown state, and the $100 stays reserved. Unknown does not mean failed. We do not release the money because it may already be on the way. We do not create a new transfer because the original may exist. Instead, recovery uses the same provider idempotency key or provider reference. We query the provider, or safely reissue the same logical operation if the provider's contract supports it. Either way, we never invent a new transfer identity just because a response was lost. If the provider confirms success, we run the normal replay-safe finalization. If it proves the transfer failed before settlement, we append one release and return the funds to available. If the evidence remains unclear, the payout stays protected and can move to review required. A timer can trigger investigation. A timer alone is not proof that moving money failed. Provider callbacks are useful, but they are not guaranteed. They may be delayed, duplicated, reordered, or lost. The callback adapter verifies the signature, records the raw event, and deduplicates the provider event ID. A repeated success is a no-op. A stale pending event cannot move a succeeded payout backward. Separately, a reconciler scans aged submitted and unknown payouts. It queries the provider by the stable payout reference and consumes settlement reports when available. For every payout, it compares the transfer identity, amount, currency, destination, and status with our payout and ledger reservation. Confirmed success applies the same unique finalization effect. Confirmed failure applies the same unique release effect. This makes repair replay safe even if a callback and a reconciliation job race each other. Some discrepancies are not safe to automate. A different amount, an unknown transfer identity, or contradictory terminal states go to an auditable review queue, while the funds remain protected. We also run conservation checks. Finalized earnings and corrections must reconcile with available, reserved, and paid effects. Every succeeded payout should have one reservation, one external transfer identity, and one finalization. Before we talk about scale, let's rebuild the complete system once from left to right. The driver sends one identified request to the payout API. One authoritative transaction creates the payout, reserves the funds, stores the request identity, and records dispatch intent. The outbox and queue carry that same payout to a transfer worker, which reuses the payout-derived provider identity. Authenticated callbacks provide fast evidence, while reconciliation supplies the independent recovery path. Balance and history projections make reads fast without becoming financial authority. At the stated scale, we partition ledger rights by driver and currency account. That keeps normal balance changes local to one correctness boundary, instead of requiring a global lock. Optimistic account versions, or serialized rights, handle contention on a hot account. Queue workers scale horizontally because each payout carries stable identities and conditional state transitions. Read-heavy balance and history traffic can use replicas or versioned projections with an as-of marker. Older immutable records can move to cheaper storage only if they remain queryable and verifiable for the 7-year audit period. Finally, financial correctness must be observable. Alert on negative balance attempts, duplicate idempotency conflicts, aged outbox records, long-running unknown payouts, provider mismatches, duplicate events, and failed conservation checks. Availability matters, but if the authoritative ledger is unavailable, it is safer to pause new payout reservations than to guess how much money can be spent. Here is the entire design in 4 rules. Reserve funds atomically before any external transfer begins. Carry stable identities across client retries, worker retries, and provider calls. Keep uncertain payouts reserved because unknown is not failed. And reconcile internal ledger state with independent provider evidence until the outcome is proven. Those choices give the driver a fast, recoverable experience without weakening the financial boundary. To practice this as a guided system design interview, open the driver payout system problem on FastPrep. You can work through requirements, entities, APIs, architecture, concurrency, and reconciliation step by step.